Okay. Thank you very much, Vanessa. So I'm delighted to present our next two speakers. I'll start with Chris Bauch, who's sitting over there right now. He's a professor at the University of Waterloo, a full professor, and University Research Chair in the Department of Applied Mathematics. He works on mathematical and computational models of the dynamics of natural systems, such as ecosystems or infectious diseases, but also with an emphasis on understanding how they interact and relate with human systems, and how that understanding can be used to improve ecosystem health and human health. So we've had a couple of questions about this yesterday and today. Earlier. His study systems include forest grassland, ecosystem mosaics, forest pest infestations, childhood vaccine scares, and influenza vaccination, among, I think, a host of others. Chris Bauch has also reached a wide public audience through the media and has been covered in the New York Times, Scientific American, USA Today, BBC News, and other sources. And I'm going to say, like, we're nowhere near there, but we also have a What the Numbers Say event coming up with both Chris and Madhur in a couple of weeks. So stay tuned for that. That's on May 17th with Vanessa as moderator. He has various research partners, and they've included the World Health Organization, the US FDA, and the Bill and Melinda Gates Foundation. And he's also a recipient of the CIHR New Investigator Salary Award, an MRI Early Researcher Award, and a Marshall Scholarship. So Chris will be presenting in the second half of this talk. I'd now go on to introduce Professor Madhur Anand from the Department of Environmental Science at the University of Guelph. Madhur is an internationally recognized ecologist with research interests ranging from theoretical to empirical studies of natural and human-induced changes in ecosystems at multiple scales, so both regional and global, and their implications for sustainability. Her research has been supported by various governments, as well as industry, national and international granting agencies, and by several awards, including the Premier's Research Excellence Award and Canada Research Chairs. She has collaborated with mathematicians, theoretical physics, statisticians, computer scientists, geographers, and poets. She serves on several international journal editorial boards and grant selection panels, and currently as president of the Sigma Psi Scientific Society at the U of T chapter. In 2011, she was named a Young Scientist of the World Economic Forum. She's presented scholarly work in ecopoetics, co-edited a book on ecopoetry, published poetry in literary journals, and was recently elected member at large with the Association for Literature, Environment, and Culture in Canada. Her debut collection of poems, A New Index for Catastrophes, which touches on several complex theory topics, was published to international acclaim in April of 2015 by McClelland and Stewart, Penguin Random House, Canada. So we have, I think that's a mouthful of an introduction, but I wanted to go through it all because it was fascinating. We're at an interdisciplinary forum, and I've always said, or always believed, that those of us who are scientists are inherently creative, not just logical, and otherwise we'd be reinventing the wheel forever. But with that, please join me in welcoming Madhur Anand.
Super. Thank you so much. Yeah, that's a CV from 2015, but nothing's changed. Nothing's changed. Let's see. Yeah, I'll just get right into it then. Thank you so much. Thank you so much for organizing this wonderful workshop, interdisciplinary workshop, Wiki, Vanessa and Dawn and Fields, Malika. I love to see the collaboration between institutes. It's wonderful, and yeah, happy to be here. So I'm going to get right into it. We're going to talk about socioclimate systems, and which form is a subset of a larger kind of system that we've already alluded to in the talk this morning in the question session, that we work in a broader ecosystem. Climate is just one component. Humans are another component, but there's this broader system that we work in. So I'm going to introduce to you some ideas around what we call, and what many people are calling now, human environment systems, coupled human environment systems. And, we're just starting as scientists, I think, to try to get our minds around these very complex systems and to look at coupling in both directions, the coupling between humans and environments, and then the feedbacks between that coupling back on human society and our decisions, behavior, and with the hopes of improving things. So mathematicians have been studying humans and ecosystems and humans as ecosystems for a long time. We have very early models that date back. I don't know how to do this, so I don't have to lean in. This is good, right? For the audio. Good. Early models of human dynamics with respect to ecosystems really date back to the 1700s, 1800s. All of you will have heard of Malthus and Verhulst and Ludwig Volterra, etc., which are the precursors of our models of human interactions, largely based on things like extraction, fisheries, etc. And that has then moved into the 1990s and into the current decades with more complex and larger land use models, common resource problems, and so on. Notably, Nobel Prize winning work by Ostrom. So there's quite a lot of history, but many of these models are unidirectional in terms of how they look at human influence on the environment. It's negative predominantly. And so the questions are more on like, how do we mitigate that? How do we reverse those trends? But there's a kind of more recent evolution in terms of how do we not just look at the negative impacts, but also the potentially positive impacts in those relationships. So that's what we've been doing. Chris and I, we started collaborating in 2010 on what we're now calling these coupled human environment dynamical systems. So I'm just going to quickly conceptually cover it in this diagram and again, this is already pretty artificial because I've put humans and environments in two different circles, but we're trying to find some way of visualizing it. And the thing is, they're linked. They're linked through feedbacks, through relationships. But, the idea is that sort of historically, and also because of how we work in academia and other parts of society where there's the natural scientists on one side and the, sociologists and everybody else on the other side, we tend to study these systems in isolation. So we have quite a large body of knowledge on how ecosystems work. I'm an ecologist. I started out as, that's what I've been doing for a lot of my career. We have lots of knowledge about the interactions, about how growth occurs and what types of models are appropriate and where thresholds happen and how to study multi-species communities and biodiversity. What are the biogeochemical feedbacks? I mean, we don't know everything and there's still so much to learn, but we know quite a lot. And but on the human side, oddly, if we do know this stuff, it's not, we scientists don't study it and we don't know it. We really don't know it. But there's a lot happening on that side with respect to social norms, social behavior, how we value things, which obviously is a dynamic thing that changes in time. And frankly, that's our only hope to get out of all of our problems. So there is quite a lot of work done on that side. Often it's done in isolation. Increasingly, people are realizing these things, but the processes and mechanisms through which these systems are coupled are manifold. So for example, oops, very sensitive. There are things that we know link these systems. Like we know that humans start to value things when they become rare. Generally speaking, there's going to be exceptions to everything I say, but generally speaking, we know that, and we can make use of that. I mean, that's where all of our legislation around conservation comes from, Endangered Species Act. That's what it is, essentially, if you boil it down. We are totally enthralled with economic benefits of environmental systems, and also we realize that there are risks. There are real risks to human well-being with these changes to the environment. On the other hand, we do need them. We need them for harvesting, and there's also so we can, and we know that, okay, so here are the actions through it that we can mitigate also as humans. We can harvest less or differently. We can protect, we can restore, and any other sort of form of mitigation more broadly. There's a whole array of things that we can do there. So Chris and I have been studying with many students, some of who are in this room today, past students who have been here at Guelph, postdocs, a large number of wonderful colleagues around the world. We've been studying these coupled systems in a variety of different problems, and our general approach is that we tend to work on areas where the ecology is well known, the science is well known, and then we try to kind of work out the human part, and then we look at what happens when you couple it. So that's the general approach, and we've studied forest systems, forest pest systems, fierce fisheries, coral reefs. I think that's everything there. And the very first paper that we worked on together, which was published, I think, in 2013, but we started work in 2011, was with an undergraduate student. And we were looking at a problem of forest conservation. So remember I said 90% of forests are lost in Southern Ontario. Well, that number is reproducible in a lot of places in the world. So this is a map of Southern Brazil, where I have been working. I had been working for many years. And this is the endangered Atlantic rainforest. It used to occur all along the coast of eastern Brazil, but of course, through colonization of South America, over 95% of it is lost. It's the most endangered forest ecosystem in the world. But small patches exist, and I was working with some colleagues over there on some of the interesting ecological questions around them, how to kind of better, learn how to better preserve what is left and maybe even restore some things. And we encountered some really interesting human dynamics in this system while we were there. That, at the time, when I was told these anecdotes and stories about what people think of these different ecosystems, I thought, well, that's really interesting, but it never occurred to me to include that information in models. And I'll tell you, very quickly, what one of them are. And this slide also serves to introduce to you, I'm sorry, I cannot stand still. Serves to introduce to you the basic assumptions that we use when we compose our human models. Okay, so these are general assumptions about human behavior that pretty much will be present in every modeling project that we do. Humans can be grouped according to their behavior as mitigators or non-mitigators broadly. So in this case, in the forest case, it could be conservationists or non-conservationists. But in climate change, it just could be, mitigators or deniers or not mitigators or non-mitigators more broadly. Humans respond to risk perception. So I've already mentioned that. And that can take a variety of forms too, right? There could be risks of flood. There could be risks of, disease, different things. Humans can learn from and influence others in their values and opinions. So that's kind of that's sort of makes sense, I suppose, but it's not something that's typically studied in ecological models. So in this case, it was really interesting in the southern Brazil situation, because what you don't see in those maps is around those forest patches are natural grasslands. And this is a very old ecosystem that kind of coexists in the forest and grasslands, sort of coexist, much like the savannas, but different from the savannas. And you know, my colleague, Valeria de Patapilar, professor there at the Universidad Federal Rio Grande do Sul, said that, you know, there are people there are very strong cultural preferences between, you know, certain subpopulations of the people who live there are very clearly they love forest. They want to preserve forest. They see the value in preserving forest. And then there's another group, and we can talk later about who those people are and why, that are like, oh, I care nothing about forests. I love grassland. And I thought that was a really interesting idea and dynamic that, you know, we could explore, because clearly that kind of preference can eventually translate into what gets preserved, right? And what the landscapes look like. So that was our very first case study of coupling a human environment system. It was published in 2013. And what I'm going to show you now is the kind of type of human side of the equation that we came up with in that model. I'll just go through the components of it very, very broadly here. But this equation will show up again and again in everything that you will see from now on in many of our papers, with slight tweaks and variations. It looks not much, but it can be quite interesting in terms of what types of human behavior you can incorporate and how that behavior ultimately affects how ecosystems are conserved, or how whatever environmental system you're working on is sustained. So what we have here is an equation where X is a certain proportion of a human population. And in this case, it's the proportion of mitigators. And so what you'll see here are this first kind of term here, which is a term that represents the social learning. And it comes from evolutionary game theory. This is an equation that Chris used when he was studying in a landmark paper that he published prior to this, looking at how imitation dynamics affects vaccinating behavior in disease spread. It's also used more broadly just to study imitation dynamics, right? So here, and another sort of term for that is social learning. So again, going back to these assumptions about human behavior, this is how humans influence each other and change their mind, okay? And how somebody can go from being a mitigator to a non-mitigator and vice versa. That happens with that dynamic and at a certain rate, constant. Sometimes we make that also dynamic, but for here, it's a constant, K, kappa. So that's that first term. And so what we tend to do in models is to vary that parameter to look at the strength of the coupling. That's one way we can look at the strength of the coupling, and just the strength of social learning, right? How does that affect things? Okay, then we have this other term, which is actually a composite of various things. We have a utility function. Okay, so remember that also we're interested in how humans value things, risk perception, stuff, economics, all of that gets put into this utility function. So here's how it can break down. There is a cost associated with mitigation that can be estimated. There is something called social norms, which can be added to these models, and that can be also studied. And gosh, I can't see my own slides. I'm gonna have to put this, there we go. And then we have something that more generally we can term the strength of response to the environment. That will include things like risk perception. So if there is a strong a concept or response or a knowledge of risk, there will be a stronger response to mitigating. So that's all represented by these functions. We can go into the details. I don't think I have all of the, let me just see if I have, well, it's not advancing. I don't have the, oh, I do actually. I'm going to show you an example of how those can work out in a specific case in a more detailed way. But broadly speaking, this is what the equation always looks like. What varies is the utility function, pretty much. So yeah, that's broadly. In the case of the example I was just telling you about, studying these forests, yes. Oh, sure, yeah. Yeah, can we save that one till the end? Perfect. Otherwise, I'll just get totally derailed. It's a great question, and we definitely will address it at the end. There'll be lots of time for questions. Okay. Yeah, the simple answer is, of course, you can add another term to the model. I don't know that we have studied that in any of our cases, but super question. Yes, I feel like the cost to inaction, see, I'm already getting derailed. Sometimes like gets, because it's a good question. I'll come back. Okay, so here we are. This is the model for that forest grassland system in Brazil and how we introduced that X equation into it, okay? So what you're looking at the top is a really simple, very well-known model of population dynamics and ecology, frankly. And here the F is forests, okay? And so the idea is that you have forests or grasslands in this ecosystem, which is the case. Increasingly, there's agriculture, but that's another story. But if you were just looking at the sort of pristine ecosystem, it's forests and grasslands, and the switch between the two can happen through a recruitment function. This is a well-known ecological dynamic where forests can theoretically cover the whole landscape if you just look at the bioclimatic situation, but they are held back by disturbance, by fire. They cannot, so they're held back. So that's what actually allows for the coexistence of grassland. So there's a bistability in this system already. But then we have to also look at the human impact, right? And so the human impact happens via harvesting of the forest. There's some natural mortality, which is this term here, but then there's a harvesting, which you can see where the X appears. So that's where the coupling starts with the human system, right? So in sort of older models, you would just look at that one way interaction, and you would kind of leave it at that, right? You'd be like, okay, there's a certain amount of harvesting happening by this human population, and we're just going to have to take that into account. And if things get bad, we just stop harvesting, and that's it. But in fact, we couple that. We create a dynamical equation for the human population. That's what that is, and you'll hopefully already recognize the form. Here you can actually see in this slide the specifics of those terms, which we can go into later, if people are interested in those details. Generally, they take the same sort of functional forms. They're threshold responses. They're threshold responses. So we've done this now in a number of ecosystems, and the question then is, like, what does this coupling do? What do we learn from this coupling? What's different? What happens? And here is what we've generally found. We've generally found that human environment feedback and social norms increase the number of dynamical regimes and tipping points compared to uncoupled models. What does that mean? Many things. It means that it adds complexity, yes, to the outcomes, but I would argue, and this is something that we kind of do show through a variety of studies, that it also allows for more nuanced responses in terms of policy. And I'll get to that sort of at the end when we talk about more broad strokes things. Another thing that we find is that human environment feedback can stabilize the environment, can stabilize it, whereas in the uncoupled state, that it does not occur as easily. So the systems can persist for longer than expected under the isolated system assumption because humans react to deteriorating environmental state. So that's what the models show. Clearly, social norms are a double-edged sword, right? What's normal is not always good. And what's majority is not always good, as we have seen many recent examples. So we have to just keep that in mind, right? If you start to put it in your models, you better be careful because you may not get the outcome you want. Human environment coupling changes the nature of early warning signals and at tipping points, and Chris is going to talk a little bit more about this. Okay, now I'm going to just very quickly show you the case, the specific example of the coupled human climate model. Okay. This is stuff that I think this room already doesn't need to hear. And this is current from maybe 5 years ago, so it's just getting worse. We've surpassed, anyway, we're not meeting any of the targets that we're not on track, right, to meet any of the targets of the Paris Agreement, et cetera, et cetera. It's a problem. There are a variety of human responses to this problem. We have seen a dramatic increase, actually, I would say, in the past decade of awareness of just various kinds of human responses, some expected, some maybe not expected, right? So climate marches, maybe we could have expected that, right? That kind of social response. Rising popularity for greenish type parties is in some parts maybe could be, if you think people are behaving and thinking rationally or in a certain way, that could become more prevalent. School strikes. For me, I found the Yellow Jacket movement, which, as you may know from the news, was this sort of response, a counter response, right, to climate change mitigation, to carbon tax, right? I found that a kind of, personally, although that probably just says a lot about me, I found that surprising as a response. I didn't quite expect that. The striking on the other side. So, there's been a variety of human responses, all to say that the norms are changing and social dynamics is very dynamic right now. Yeah. And so just more of sort of what the trajectory has been looking like, which I think you all already know. Now, the standard approach to modeling climate change is to consider fixed CO2 emissions trajectories, okay? Whether you're looking at complex models or simple models, that's the standard approach. I'm not saying people are not doing it, but generally that's what it is. So, these are the types of responses you see. There's a scenario that's outlined, and there's a variety of scenarios, and you can say, well, here's good scenario, here's best scenario, here's status quo, here's not doing enough. And then we just project the, global climate change in terms of mean annual temperature, et cetera, and emissions, which obviously translates into that. And they're based on geophysical models where, climate dynamics is fairly well understood, though there's lots of nuances there, of course, as well. And so emissions translate into temperature change. That's a kind of well-known approach and standard approach to looking at how humans impact climate. Very few models incorporate social climate feedbacks, surprisingly, there's a few groups doing it now. But at the time when we started to, actually, it was not even, it was sort of an extension to our human environment work, to be honest. Like neither of us work on, I mean, I work on climate change as an ecologist in terms of response, but not per se. But we thought, well, if we can study like human ecosystem dynamics, like why not human climate dynamics? And so that was the idea. It was really just extending that to another case. So the diagram is kind of similar to what I've shown you about human environment systems more broadly. But the feedbacks are very specific related to climate. So what we did with a PhD student here at Waterloo, Tom Burry, was to do that. That was his PhD thesis, part of it. And he found a relatively simple model of climate dynamics published by our now colleague, Tim Lenton in the UK. I think I have the whole model here. Yeah, this is the model that Tim developed, which does a pretty good job of predicting, sort of replicating what more complex climate models do. We need to work with simple models for our approach, or at least initially. But, you know, we've been now working with colleagues here on some more interesting, other more complicated models. But yeah, we just started with the simplest we could think of that was pretty good. And then again, you know, with the social system, it's all of the same types of dynamics that I've already explained. So it translates into this set of equations where there's a few things on the environment side. Atmospheric, this is Tim Lenton's model, you know, atmospheric carbon, oceanic carbon, vegetation, etc. And then there's you know, these all translate into temperature change. And then this is our equation, which you all recognize now. What differs obviously is how these parameters work, and we can discuss that later. Mitigation costs could be different, but it has all the same components. We coupled it, and here's what we found. Okay, so typically these are the types of graphs that we produce. We change a parameter. We want to look at the effect of some aspect of the model on the dynamics. So if we want to look at the, so generally speaking, look on the right here. This is a sensitivity analysis of all the parameters in the model. Okay. So you can sort of see their mean values, and then you can see how they affect peak temperature anomalies. And then you can obviously look at the variability, right? How big those bars are on each side. So an interesting thing was that the social parameters in the model, which are indicated here, had a strong asymmetric impact on the projected peak temperature. And generally speaking, like when you compare the social parameters to all of the environmental parameters, had orders of magnitude greater impact on the temperature anomaly, 1 order of magnitude, which is hopeful, right? If you're following the line of reasoning. Climate change is, you know, the rate of, we can change the, we can have a great impact as humans, essentially, by changing our emissions trajectories, is really what that is saying. Okay. Then if you break it down and you want to look at how each of these components contribute to the model, which is always interesting, the rate of social learning between empirically plausible ranges varies the peak temperature by more than 1 degree. So we can change it profoundly. I mean, this is the hope, right? Social norms initially suppress mitigative behavior, delaying the transition to mitigated behavior. So we have to be careful if we're going to be doing some sort of policy work around this. Reduced mitigation costs have little effect unless the social learning rate is high. So this is interesting. Yes.
Sorry, previous slide.
Previous?
Yeah. What is the y-axis?
The one with the graph. This one?
Yes.
Oh, you mean this one we're talking about? These are each of the parameters in the model. Each of the parameters. So yeah. right? So here is social learning is this kappa here, right? I don't know. Yeah. So yeah. Yeah, it was a fun way to look at that. Red versus blue, good question. Positive. Yeah, you would think they would all be red and blue. I can't remember. Do you remember, Chris?
One color was the increase that parameter.
Oh, yeah. Yeah.
I can't remember.
Yeah, I can't remember. But the directions. Yeah, anyway. The magnitude, yeah. Yeah, it just has to do with the causality. Like if you increase the parameter, does it increase temperature? If you decrease the parameter, does it decrease? Something like that. Yeah. Yes, this is really interesting that, one of the findings of this potential policy implications is that you really have to look at more than one factor. It's not enough just to reduce mitigation costs. And those are the kind of things that you can study, So what order do you have to do things and what's the relative importance of these? So, yeah. And then there was a high sensitivity to forecasts. I won't go into that. That's a little too much detail. So let's see, 11:30. So I think I've gone over some of these. Yeah, so this is another thing, as I said, you can look at parameter planes, right? So you can look at more than one parameter and its impacts. And one of the interesting things that came out of this was, not something you can think out, like, is what is the optimal trajectory, right? And what we found was that, first of all, the combined effects, it was important to look at the combined effects, but some of the increasing social learning was most effective initially in terms of having kind of the most impact on the trajectory. Reduced mitigation costs were effective, as I said, only when the social learning rate is high. So this is social learning, this is net cost of mitigation. You can see the effect on the combining these and the rates of these on the temperature anomaly. And basically that to achieve our climate goals, intervention targeting multiple aspects of social processes were required. So I think I am going to, we've done some additional work on kind of looking at various aspects of the human population, because right now you'll notice that we just very coarsely divide things into mitigators and non-mitigators, but it's very complex. It's a very complex societal problem. And so we wanted to look at the human population a little bit more realistically by considering, for example, the socioeconomic divisions in society and how that could impact behavior. So we've done that also with another project. I think I'm going to, we know that we're going to transition now to the second half of the talk that Chris is going to take over, and he's going to look at tipping points, because these models all generate very dynamical instabilities, and there's a lot of places where tipping points can happen, and you're probably hearing a lot about tipping points in the media. They can happen in the climate system, as indicated here and studied. It can also happen in the human system. So he's going to show you some work on that. I'm going to, how much time do I have roughly, Monica, for my half?
25 minutes left.
Okay, so I'm going to quickly transition. I think Chris is going to show you this. I wanted to end on this slide, which was kind of an interesting thing that had never happened to me as a researcher, which is just a funny phenomenon that I think we need to come up with a name of. When the media picked up on that study, when it was published, it was quite popular with the media. But look at how they picked it up. Like, just read some of those headlines. This is just the study I just told you about. How to fight climate change. Let's talk about it. Social interactions can help slow climate change. I think my favorite is how to fight climate change. Let's just talk, all we have to do is talk about it. Honestly, I love it. I love it because essentially that's what the model is kind of telling us to do. If you reduce the concept or idea of social learning, I mean, humans learn through a variety of different ways, but a very important way is by talking to one another. And whether it's in person or whatever networks you have, social, different things happen in different realms. But yeah, I just thought it was so funny to see media enacting the actual outcome of the research, like a positive feedback right there. I did not predict that. And we had to do many radio interviews where like, so you're saying we just have to talk about it? And like, well, yeah, kind of, yes. And to be honest, even to this day, because we get asked it again and again, what do I do? What should I do? What can I do? What is your advice? What can I do? And I'm just getting so tired about giving the same list of things that everybody knows, right? So I actually just say, you know what? Let's talk about it. What are you doing? Just talk to people, talk to your neighbor, So anyway, it's an oversimplification, of course, but it was just such a funny thing and a great use of media for sure to enact the research. So I'm going to turn it over to Chris now.
Okay, right. So as Madhur was presenting in the first half, a lot of our models have been relatively simple, in fact, and we think this is an underutilized style. Simple models have a lot of value for clarity, and they're often more predictive than you might think. But of course, they aren't perfect. We had this kind of spaghetti of other processes that can happen both in these systems separately, but also in their interactions, which if you're looking for a predictive value, like if you want to know what the temperature will be like in 5, 10, 20 years, maybe you need those details for some cases. And of course, this can also influence aspects like tipping points. When will we reach them? How can we detect them in advance, etc. So the first half was what you might conceptualize as a deductive approach. So you hypothesize some mechanism, you construct a model and you analyze it, and then you compare it to the data. So this is the way we usually approach modeling. But one could also posit or use an inductive approach, whereby first you choose the data you want to study, the system, and then you infer the model from the data using, for example, model discovery algorithms, etc. And then you test it out a sample to see if it's actually doing what it's supposed to do. So the second half of the talk will cover an inductive approach, which is intended to deal with some complexities of real systems. This is really about complex systems with simple dynamics, and it's based on certain results from mathematics, like the center manifold theorem, which states that if you have a very complex higher dimensional system, for many cases, it will collapse down onto a subspace, a lower dimensional subspace that is simpler and perhaps more comprehensible. And you can kind of see that. Oh yeah, that animation was running here for a second. You can kind of see that far away from the center, you have these more complex dynamics going on. But as you converge into the equilibrium, it all reduces down to dynamics on a line. This is the center manifold theorem. And concerning tipping points, particularly close to a tipping point, dynamics will simplify into one of a number of archetypes. We call them bifurcation normal forms. There are only a certain number of ways that you can go through a tipping point. subject to certain assumptions about the system being well behaved, et cetera. So this is going to be the way that we're going to tackle these very complicated systems. In particular, we're interested in the critical slowing down phenomenon, which, as many of you know, is the feature by which, as a system creeps closer and closer to a tipping point or a bifurcation, certain statistical indicators change in similar ways across different systems. So for example, in the left-hand side here, we have a state of high resilience. So that's far away from the tipping point. And if you have a ball at the bottom of the valley, if you give it a kick, it's going to settle down quickly. So if we plot that over time, we see that the state when it's kicked reacts quickly and stabilizes again. And there's not much variability if in the presence of noise. So this is a highly resilient system. But as the landscape changes, we reach a state where it takes longer and longer to recover from perturbations. And if you add noise to the system, it wanders around much more widely. The variance is higher. And so as you approach the low resilient state and eventually the tip, you'll see an increase in variance, lag one autocorrelation, and the coefficient of variation. And this is universal, applying to a range of systems. For example, it's been applied to everything from lake eutrophication to epileptic seizures, and of course, climate shifts, paleoclimate shifts in particular. So, so we think that this universality of dynamics near tipping points might be a way we could tackle some of these complexities through critical slowing down. So we started this program recently, and our focus, of course, for this meeting is climate systems. Yes.
That was in my mind. I started thinking of that term in terms of numerical simulations.
Yep.
Like the one part of critical slowing down.
Yep. That's the same thing. Yeah. So you can see critical slowing down in Monte Carlo simulations, spatial agent-based models. It basically becomes stickier and more variable, close to the equilibrium before it just collapses or changes state, changes phase, whatever the case may be. Yeah. Okay, so these systems show this variability, and could the climate system be wobbling? So on the right-hand side, we've seen evidence for this wobble in ice cores for previous paleoclimate shifts. And panels A, C, E, and G show the data leading up to a climate shift, and then the gray area is the region of the shift. And you can see the sudden transition in every case. In panels B, D, F, and H, you can see an increase in lag1 autocorrelation, which is signaling that shift well before it actually happens. So this is work from 2008 by Dacos and colleagues. And of course, the modern climate is becoming more variable, as we all know, more extremes more often. So the climate system might be showing these signs of critical slowing down potentially. Now, many of these commonly used statistical indicators like lag1 autocorrelation and variance have some limitations. They may provide false positive, which is a problem. They have limited ability to determine the type of bifurcation that's approaching. Now, if you're talking about the global temperature anomaly, maybe it doesn't matter because we know it's going to go up the temperature. But at a regional scale, we may not know as much. And so if the lag1 autocorrelation is increasing, it's heralding a change, but we don't know what change that might be. And they can also be difficult to attribute statistical significance to changes. On the other hand, deep learning algorithms have achieved state-of-the-art in time series classification. So for example, a Fitbit, if you're wearing a Fitbit on your arm, it looks at your heart rate and motion, and it can infer whether you're on the elliptical or running or whatever. So Madhur and I thought, well, maybe we could use these types of approaches to these critical slowing down time series. And perhaps it will also excel when it comes to classifying time series of climate, for example, or lake eutrophication. But there's, so in particular, the algorithm might detect the signature of higher order terms that are normally thrown out in analytical approximations used early warning signals. So what I mean is that, this kind of potential landscape you always see, the mathematical expressions we use from this are always first order terms of a Taylor series expansion. And those terms are the ones that indicate variance and Lagrange autocorrelation are going to increase. And we use them because they're easy to compute, they're mathematically tractable, they're really nice to work with. But you're throwing out a lot of information because it's messy and system specific. And it's ugly to our mathematical aesthetics, actually. But deep learning doesn't care about that. It will very happily look at those ugly terms and tell you what's going on with them. So we thought, well, maybe it can detect these higher order terms that we normally ignore or throw out. And maybe it can also tell us what's going to happen after the bifurcation, because many of these bifurcation normal forms have the same first order terms, but they have different second order terms. And so maybe you can distinguish, for example, a collapse versus a smooth transition, a fold versus a transcritical. Okay, but here's the problem. Deep learning algorithms require lots of time series. Like if you want to classify pictures of cats, you need thousands of pictures of cats, right? And we only have one climate system, and this is the first time we force it in the way we're forcing it. So what do? We have not enough data to train these algorithms. So what do we do about that? So we had two hypotheses. The first hypothesis was that if we train a deep learning algorithm on a sufficiently large training set generated from a sufficiently diverse space of models, the features of any empirical system approaching bifurcation will be represented somewhere in that training set. Therefore, the algorithm can detect early warning signals in systems that are not in the training set. Okay. Second hypothesis is that the algorithm will detect early warning signals of a bifurcation sooner than existing approaches like Lagrange autocorrelation, as well as tell us what type of transition is occurring. Okay, what that means is that even if you have a relatively limited training set, but I'm still talking about 100,000, that might contain the right kinds of features that characterize the higher order terms in the real system. Okay, so we're going to exploit universality to do this. They rely upon universality, the idea that complex dynamics simplify close to a tipping point because of the central manifold theorem and bifurcation normal forms. So this work was led by our joint PhD student, Tom Burry, and published a couple of years ago, along with our co-authors. So we approached, just briefly, we generated this by generating a huge random library of mathematical models with different types of transitions, fold, which is a collapse, hop, which is oscillations, transcriticals, that's what I mean by branching point, and no bifurcation. And then we trained some vanilla run-of-the-mill a deep learning network, CNN LSTM, to classify them based on the pre-transition period. And then we tested the algorithm out of sample on a bunch of different training sets, both empirical and models from various systems. And I'll say more about those, but we also included that paleoclimate data. And neural networks, they're basically huge statistical models. So if you understand some stats, you understand neural networks, sort of. What you don't understand them well enough to learn it from a blog and do it. But briefly, the way this particular network works is that it's a combination of CNN and LSTM. So the LSTM is long short-term memory. It kind of rewires itself in the later layers back to the earlier layers, which means that it can kind of look backward in the time series and see, okay, well, what's happening when this time series is the variance or whatever increasing, or something else happening. And then the convolutional part, it kind of scans over the picture, and then does some convolutional kernels, and then translates that into features which will tell it this is a cat or this is a dog, for example. And so here are the systems we used. We used some ecological models. These are classic models, well studied for harvesting, consumer resource problems. We looked at this coupled human environment model for vaccine behavior. And then we had empirical systems. The proof is in the pudding, right? So can it predict empirical transitions? We had some beautiful thermoacoustic experiments from our colleagues in India, where they apply voltage to a system, and as the voltage is increased for certain temperatures, it produces sounds, and they observed critical slowing down in those systems. We looked at these paleoclimate shifts, 7 different shifts from ice cores. And we looked at Mediterranean sediments capturing the transition between oxic and anoxic states in the Eastern Mediterranean provided by Reichert and colleagues. So, and so basically this is the type of output that you get. So for example, across the top here, we have the raw time series after they've been detrended for fold, hop, transcritical, and neutral, no transition. And then the second row is the deep learning prediction, the probabilities it assigns to different transitions over time. And as we get closer to the transition on the right-hand side, we hope that the algorithm can become more confident in the right answer. So for example, fold is blue, hop is orange, etc. And as you can see, for example, in the fold bifurcation, at first it thinks nothing's happening, but then as you get closer, it realizes, there's a fold bifurcation approaching, and then it assigns a higher probability to fold, etc. for hops, transcritical, and neutral. And then we have variance and Lagrange autocorrelation in the third and fourth rows, again showing that characteristic increase close to the bifurcation as they should. So that's the way it works. As you've shown more and more of the time series to the algorithm, it can figure out what type of bifurcation is approaching and assign a probability to it. Whereas, variance, it just always increases. Lagrange autocorrelation, it just increases. It doesn't tell you if it's a fold or anything else. And then to analyze, it's not enough to look at the probabilities of a real transition. You also have to rule out false positives. So we use ROC curves, which are basically a plot of the false positives predicted by the classifier versus true positives. So these are used, for example, in diagnostic tests, etc. And what you want to see for a good classifier is you want this curve here to hug the upper left part, because it means that for a wide range of thresholds of discrimination of the classifier, you're having a very low false positive rate and a very high true positive rate. So not too many false signals. So we looked at everything through this lens of ROC. So for the simulation models, that was the easy thing for the classifier. In all cases, so here we have blue. The algorithm is in blue here. That's its prediction. Variance is in red, and Lagrange autocorrelation is in green. And as you can see, all of the classifiers do okay. The machine learning algorithm does best for all the ecological models. And so because they're nice, easy simulated systems, that's not surprising. For the thermoacoustic experimental data, it does a fantastic job again. So it's really low false positive rate, high true positive rate, and it's predicting a hop. And it's almost got 100% area under the curve. The Eastern Mediterranean anoxia data, it did even better, which surprised us. So it predicts this almost perfectly without any false positives. Variance also does well, and Lagrange autocorrelation is quite poor. So it's doing well there too. And once again, I emphasize that the algorithm has never seen this data set. It's just seen a random library of simulated models. For the coupled behavior disease model, this shows a very interesting effect. None of the approaches can predict it if it's only looking at infections over time, but it can predict it if it's looking at the social variable. So that's another concept that we've thought about and kicked around. Like, can you actually monitor environmental states by looking at the social systems that it's strongly coupled to? And we have often more data for social systems through Twitter, etc. So I'll skip ahead to the paleoclimate data. So disappointingly, maybe, the algorithm struggled with the paleoclimate data the most. In this case, all three approaches really struggled. I mean, they had some classifying power, but it could really have done better. So what's going on there? So current work with our postdoc, Dan Delusky, is trying to improve these systems specifically for climate prediction. And Daniel's been taking the approach of spatial models, borrowing from physics, in particular models that capture magnetization across a domain. And you can have these phase transitions in two-dimensional systems, for example, water to ice, or in the case of magnetization, as you apply a magnetic field and you cool down the metal, the local cells will start to line up, and hopefully, if you've done it right, your magnets will all point in one direction, and you'll have a magnet that works to stick to your fridge. Otherwise, you end up with something like this, which is somewhere in between. So briefly, the main change here is that we're looking at phase transitions, which are very different. We're looking at a spatial domain. And what that does is it says, well, okay, maybe we can apply this to regional climate systems. Look at the Amazon, for example, look at the circumpolar gyres, look at the collapse of the thermohaline circulation in the Atlantic Ocean, etc. So this is ongoing work, and Daniel talked about this yesterday, I believe. So this might already be out of date. Sorry, Daniel, but so our focus has really been on terrestrial vegetation systems, and we're using the same approach to train the model on a huge library of outputs from easing models, and then test it on vegetation systems, a simulated system, a sea ice percolation model, which captures melting of ice, and also the CMIP5 simulation. So that's a massive library of transitions from various climate systems. So here are a few examples. We see, for example, for vegetation systems, that the classifier is doing pretty well. This is an ROC. The classifier is doing pretty well in predicting those transitions in the simulated vegetation systems from Kefi et al. Without too many false positive, and also for sea ice percolation, it's doing pretty well. So how about the CMIP5 models? And those have all kinds of obscure acronyms like F goals and CMCCCSM, which doesn't really roll off the tongue very well. But anyway, so from this huge library of models, it has more of a mixed record in predicting transitions in these diverse climate systems. So Daniel looked into these systems and figured out, well, what exactly are they modeling here? And if you break it down by the type of climate system, you start to see some patterns emerge. So green are terrestrial models for terrestrial climate shifts. Orange is the land cryosphere. So Greenland ice cap, for example, Greenland ice sheet. Blue is atmospheric transitions, and red is the ocean cryosphere. So the Arctic ice cap. And as you can see, it's working pretty well in the case of second order phase transitions for the terrestrial system. So another reason to focus on the terrestrial situation. So we're interested in looking at the Amazon and the Sahel in Africa, both of which have nice data, and and in previous studies, they might show some of these features of tips. So just now a bit of discussion and conclusions apropos the second part of the talk. What we're trying to do here ultimately is create a new line of evidence for thinking about climate change. So what we have on the vertical and horizontal axis here are, for example, one line of evidence are these hugely sophisticated mechanistic models, generalized circulation models simulated on massive machines based on, for example, Navier-Stokes equations. So here we're putting in the state of the art about our knowledge of physics into the simulation to predict what temperatures will be like, how circulation patterns will change over time. The pros are that it's mechanistic and predictive, but the cons are that you can never know if you're including all the relevant details, and it's harder to validate because we've never forced a climate in the way that we're doing right now. So we also have empirical data like the paleoclimate shifts from the ice cores. So the pros are that it's actually an empirical system. You can look at the past shifts and say, here was a transition, here was what caused it. But the disadvantage is that the nature of forcing is now different from what the previous tips were caused by. So this third axis we're trying to develop here is based on the idea that the answers about what will happen is already present in the noise that's around us right now. We just have to be able to read it. And for that, we think machine learning on bifurcation normal forms might be a way to do that. The pros are that it can predict based on the present noise, and you don't need data from the system. The cons are that you need a big enough bifurcation library, and you have to be sure that bifurcations relevant to the climate system are in the library. So so I'll come back to that momentarily. So here we're trying to turn conventional wisdom on its head. So like I mentioned, deep learning normally requires massive data sets. And here we're saying that actually you don't need any data from the system you're studying to use deep learning. But this approach is not a magic formula. The bifurcations present in the empirical system must be represented in the bifurcation training set. Otherwise, the answer is basically gobbledygook. Okay, The corollary is that subject-specific knowledge is still required. You know, so sorry, Google, you can't just brute force everything. You still need experts who are not software engineers. And not, you know, you need experts both in math and in the climate sciences. The other thing that comes up when we think about deep learning is, you know, isn't AI just a black box? You know, maybe we shouldn't do this because we can't get insight. So I would say actually that we're looking for a gray box in this situation. And the inspiration of that comes from AlphaGo. Some years ago, you might have heard that Google's Alpha was able to beat the best humans, which maybe that's not surprising. But what's interesting is that the humans then started to learn from AlphaGo. So the humans learned strategies that no human had ever thought of, but they then incorporated that into their gameplay. And I think this is kind of the biggest area of benefit for looking at AI is not brute forcing stuff, but actually more nuanced and sophisticated approaches that hybridize machine learning with dynamical systems, mathematical modeling approaches. A, because it'll work better. Hybrid mechanistic statistical models often work better, just a priori. And B, you need that subject-specific expertise. In our case, for example, to make sure your bifurcations are represented in the training library. So it's more like a gray box where, you know, you don't understand everything that's going on, and you can't and you never will. And but you understand more than you would have otherwise with a purely deductive or mechanistic approach. Yeah, so in conclusion, in the second half, we've talked about, you know, this inductive approach, and we've seen that combining machine learning and complex systems theory can give us, you know, we hope more advanced warning of climate shifts, maybe at a regional scale, with better specificity than existing approaches based on autocorrelation and lag 1AC. But there's still a lot of work to be done. What transitions do we include in the library? What algorithms are best for climate systems? And actually, you could probably fill 2 slides with unanswered questions about this problem. So thank you very much. And I guess we'll have some discussion now about both halves, right? Yeah. Why don't you even 2 cups of water? That's very thoughtful.
There's some online ones, I imagine. I had a couple of questions, but maybe first for Chris. I thought it was really interesting because I come from a group where we do quantum matter research, and so we do stuff that is extremely similar. We use also all types of machine learning methods, including CNNs, but also Monte Carlo and quantum computing and stuff like this to study Isaac transitions and so on. And I also like Daniel's talk yesterday, but a question I had after that talk, and it was a little bit clear, but I thought I'd follow up on, is there like a list of early warning signals that people have agreed on, like these are the 5, you know, observables we look at, you know, just like, you know, I look at magnetization or susceptibility or something like this in a condensed matter system. Is there an equivalent of this for climate systems?
Yeah. So the question was, is there like a common list for early warning indicators in a variety of systems? And, you know, there's not really, there's rule of thumb and there's bits of knowledge here and there. I mean, lag and autocorrelation and variance are the 2 big ones, but there's also various system specific indicators. For example, sometimes you might want to look at the entire power spectrum of a time series to infer information from that. So I would say there's an agreed upon list at all. Although lag and autocorrelation and variance are the kind of the 2 big names that appear across a lot of studies. Yeah.
But I'm wondering, are you asking like about are you asking about methodological approaches or actual sort of conceptually observed or whatever, like observe? I have a feeling you're asking about the observed.
Yeah, because when we look at, you know, phase transition.
Yeah.
Models,
Yeah.
systems, you know, we look at that's magnetization. How, as we were saying, how do the the spins collectively behave. If I tune this parameter, let's say the external magnetic field or something like this, it's a very simple toy model, and then you look at this one observable, and
Right.
you see at this critical point, I get this type of behavior. And so I'm trying to
Right.
understand whether there's similar.
Yeah. So what are the observables
Like,
and analogs? Yeah, yeah. Well,
Skies, I'll look at
yeah.
temperature, I'll look at water levels, and
Mhm. Well, a very famous example for lakes is, because that's studied a lot in lake eutrophication. So the observable is the, I think it's the rate of, well, it's either the nutrient level or the response of the algal, the algal bloom, like the shifts, right, from, so the input is, I think, nitrogen. So the observable is probably the nitrogen, the thing that you're measuring, but then it shifts state, or it could be just the algal bloom itself, right? It will be in a non-eutrophied state and then a eutrophied state, and it happens very suddenly. And then you can see it in that. Let's see, Fred, you probably can give us, you've written a whole paper on this. There we go. Yeah, there is.
Where transitions happen in
Yeah.
different systems. And one step removed from that would be what are the measures in
Yeah.
that system in grasslands, and when they're a little bit different by system.
Yeah, and it depends also what's possible to collect, because they're field systems, you may not be able to get every variable, and some are more convenient to get than others. Yeah.
Like in our systems, it's like the human rate of change, social learning rate, like that's the observable that we measure, and then that can be, yeah. Sorry.
Yeah, so I'm just going to start enjoying the lunch hour already, so we'll give it 4 more minutes, and if you do have further questions, please use the lunch hour.
There is a question here too.
So, okay. So, one more, we have another motion.
Sorry, I mean, I can use it for later, but because it's more mathematical question. So both your, the original model for forest and for humans had a natural upper bound of 1 and 0. But what happens if they're not, because there is no 100% forest or 100% humans going to do that, or 0% of either. So the natural bounds are not 0, 1 in reality. So if you put a bound that's not 0, 1, and if you have stochastic parameters, what would your solutions, especially in terms of problems? Will they actually work?
well, what work? Well, what work, the models?
Yeah.
Well, I mean, what does it mean to say a model works? Can it run?
The thing is, you have to check that because in the real world, it will be not 0, 1. And so if you do that, and if you look at the solution, I'm pretty sure it's not going to give you these simple ones. So it's for you.
Go ahead.
Go ahead.
Yeah, I mean. Yeah. Okay, so there was that question from Fred, I'm not Fred, Fritjof. It was, if he's still
Inaction,
here.
cost of inaction.
Yeah, it was great question. Where would we put that in the model? Because we tend to only look at one population. So we look at the cost of mitigation, so cost of non-mitigation.
No.
Yeah. The question was, there are costs to, essentially, there's costs to non-mitigating. Yeah, cost of inaction, which is like the cost of not mitigating, yeah. Oh, yeah, thanks. Future costs and risks. Yes, we did. We have added discounting. I didn't have time to talk about it, but we also looked at discounting in that paper. Which, I mean, yeah, I mean, the basic thing is that, yeah, it matters how far in the future you have to look and how much time you have to respond as well. And things like that, yeah. Oh, what I mean is that the inaction adds to future cost. It does. And so then when you add the discounting factor, you can do different things because there's different ways that you can model discounting. And from what I recall, like there's different ways in which you can look at the like the rate of decay of it over time, for example, right? And so then you can examine the impacts of the degree of like inaction on the future or action on the future. We've looked at the degree of changing action on the future, but you could also look at the degree of inaction. Yeah.
Right, thank you, Dib. So we'll break for lunch now, and we are to meet at
1:30 upstairs in the same two rooms, 2003, 2007. Make sure you know which topic you're hoping to join in for. I do have a copy of the agenda at the registration desk if anybody needs a refresher. And then just before we conclude, we just have a small gift for both of you. Thank you very much for taking your time to join me.
Oh, I keep saying you're getting two for the price of one, but you're not. Thank you. Oh, I'm sorry. I think about the guests. I'm sorry. I was probably very like. Yeah, you can come in too.
Thank you.